All right. Great to be able to join CogSci, even though I couldn't make it to Toronto. So today I'm going to share some recent empirical and computational work that my collaborators and I have been doing on the mechanisms of learning through practice and reading examples. So every time we teach or design instruction, we make lots of decisions, and so do our students. One such decision is whether instruction should focus on practice testing or studying examples. Let me show you what that looks like. So students might be asked to generate solutions or solve a problem or generate the rest of a sentence or a word pair, and this would be considered practice testing. Another possibility is that students might be shown the solution to a problem or the steps required to solve a problem or the complete sentence of or both words in a word pair, and this would be studying examples, right? So understanding the cognitive processes involved in each type of instruction, practice testing or studying examples, is important because it provides a window into our cognitive architecture, but also is practically important because it allows us to fine-tune instruction to yield the best learning outcomes for everybody. With that in mind, of these two approaches, what is the best way to learn, say, the formula for the area of a trapezoid? Well, one way, one could learn it by practice testing, starting with a study session, and then repeatedly practicing retrieving the response. Just a question, now the formula is not there, you retrieve it and do this a few times. Practice testing like this has been shown to be a generally powerful learning strategy that would probably improve learning the formula of the area of the trapezoid, which is what we are focusing on right now. And the proposal is that practice testing delays forgetting and improves later retrieval of the information that you keep practicing and retrieving. But what if instead of retrieving the formula, we want to learn to calculate the area of all the trapezoids and not just memorize that formula? Well, one possibility is to also use testing. So you start with an example, you have a specific problem about a specific trapezoid, you apply the formula, and you have your answer there. And you see that example, and then you keep practicing with different trapezoids, and you keep practicing and practicing. Although I would say that the evidence is pretty clear that we remember the formula for the trapezoid area better using practice testing, it is perhaps not as obvious that our ability to apply it will improve as much by only practicing without seeing the examples. A lot of research with these types of materials, applying formulas or calculating areas, suggested that studying more examples can actually improve learning. And one might ask, okay, how do we reconcile these two potentially contradictory proposals, that you should practice more, that perhaps you should practice less, and find the best way to learn different types of materials? Some in the past have argued that examples should be used with complex materials and testing with simpler materials. However, there's two problems with this. One is that this proposal does not seem consistent with some of the empirical evidence out there. And perhaps more importantly, it is hard to define what the complex material might or might not be in a consistent way. Instead, our proposal is that practice testing improves memory and delays forgetting of encoded information. However, studying examples improves induction and refining through selective encoding. Selective encoding is not always going to be necessary, but when it's necessary, stopping practice and instead studying examples will actually improve learning. So how do we know if induction and refinement are necessary or not? As I'm sure you will agree, not all materials we can learn have the same selectivity requirements. So say, for example, that you're learning facts, such as the formula for the trapezoid. After an initial study of the question and the answer, all subsequent tests include only the relevant information that needs to be encoded and remembered, right? It's just the name of the shape that you need to memorize the formula for and the formula. So when learning facts, there is no selectivity constraints. Every single piece of information that you might have memorized is probably important and likely to be useful if you retrieve it later. But when learning skills, such as learning how to calculate the area of the trapezoid, all tests include new details. Some of those details are relevant and others not so much. So you will start with seeing an example, a particular trapezoid and how to calculate it, and then you might see a problem without a solution. And now it's a completely different trapezoid with different kinds of information. Perhaps it's in numbers, but also more details or fewer details. And here there is a clear need to select what to encode, and encoding and remembering all of the details might be detrimental and actually delay learning. So when learning skills like this, there are selectivity constraints that are created by all the irrelevant variation that happens from problem to problem. So we ran a laboratory study to test this hypothesis that whether we should practice more or study more depends on the selectivity demands of the to-be-learned materials. So in this study, after the pretest, participants were divided into 4 conditions in a 2x2 design. They either practiced or they studied either facts or skills. All participants learned 4 concepts: the area of the circumference, the area of the rectangle, the area of the trapezoid, and the area of the triangle. If a fact version if they were in the fact version condition, they learned the formula for each one of these geometrical shapes. If they were in the skill version, they learned to solve problems with different geometrical shapes. Another thing that I want to point out here is that both conditions include some study trials and some practice trials. In the study trials, the question and the answer were presented, and in the test trials, only the question was presented. What we manipulated is the relative frequency of each type of trial. Practice training includes 1 study trial and 3 practice trials, and study training includes 2 study trials and 2 practice trials. And the content was matched across conditions. After training, participants completed the structure task, and then they completed a post-test. Getting to the results, participants overall performed better post-test than a pre-test. So here, what I'm plotting on the y-axis is the pre-post change after learning facts on your left or skills on your right. And each color bar that is going to show up represents the different types of training, either practice or study training. So if our hypothesis is correct, we should see an interaction here, right? With better learning of facts with practice training and better learning of skills with study training. When learning facts, participants learn more during practice training than during study training. And this replicates the benefit of practice testing that I told you about in the beginning and that is evident in the literature. Conversely, when learning skills, participants learn more during study training than during practice training. This also replicates the benefit of studying examples that is evident in literature, but more importantly, this pattern of results is consistent with the hypothesis I set out to test. Examples improve selectivity when needed, as is the case when learning to apply the formula to different kinds of materials. So learning to generalize the formula. But of course, this could be a one-off situation. Maybe it's not about the selectivity requirements or memory constraints. Maybe it's just about formulas and about geometry, or the fact that they already knew some of this to begin with. So we repeated the experiment, changing just a few key parts. The most important thing we changed was the stimuli that we used. We kept the distinction between facts and skills, but they are now made up math, things that participants could not know before coming to the lab. So when learning facts, participants are learning to pair a number with a question. So 2 diamond 5 is 23. This is definitely a fact. There is no way to learn how one gets to 23 from here, as there is no information on how it's calculated, like with the formulas in the previous experiment. So when seeing an example, participants see the question and the answer as you see on the screen. And when practicing, they only see the question. And it's always the same question because it's always the same fact. When learning skills, participants are learning how to solve the same kind of question. So to solve that 2 diamond 5, one needs to calculate diamond to the power of 5 and then invert the numbers. That is where your 23 comes from. Here, there is no need to memorize the answer. You can always solve to the solution if you know how to solve it. So when seeing an example, participants see the question and the steps to the solution, as you see here. And when practicing, they see only the question, but always a different one, because the job here is to learn the generalization, not memorizing numbers. All right, so the rest of the procedure is very similar with just some minor procedural changes that I have here on this slide. I'm happy to discuss the different changes in procedure if you are interested later on. Getting to the results, because there is no pretest here, I'm plotting final test performance on the y-axis. And on the x-axis, I'm plotting whether training was study or practice-based for facts on your left and skills on your right. So for facts, participants performed equally well regardless of the training they got. And this is perhaps not surprising since they learned only 5 concepts, which means that they needed to learn only 5 answers to 5 questions. So it's relatively easy to memorize and to learn. For skills, on the other hand, participants performed better when they saw more examples during training than when they practiced more during training. So again, overall, these results are consistent with our hypothesis and the results of the previous experimental geometry problems that studying examples will help learning when selectivity is necessary, when there is multiple pieces of information that you might memorize that are erroneous, and you need to learn what to ignore. Okay, so I have empirically demonstrated the effect. How can we specify the computational mechanisms and can it yield similar results? Well, verbally, I hypothesize that practice testing increases memory and delays forgetting, right? I said that in the beginning. And that studying examples increases selective encoding. And so it's going to be helpful when that selective encoding is necessary as when learning skills. I implemented these ideas as part of an AI system of simulated learners called the apprentice learner. These AI agents are able to perceive the world through an interface and learn by memorizing and extrapolating information from repeated opportunities to learn. The infrastructure is open source and can be used by anybody. I really encourage you to go poke around. One advantage of using AI here is that it generates behavior with zero parameter feeding, which will allow me or anybody else in the future to test different manipulations with no or very few human participants. OWL learns by induction from examples and has a memory mechanism in which practice delays forgetting of all the information encoded as I hypothesized there. So I simulated 95 agents in a setting similar to the geometry experiment because we want to match that. And because human participants in that experiment probably had some knowledge of the geometry content, I pre-trained each agent to be at the level of a corresponding human at pretest. So each one of them has now some knowledge similar to a human participant. So as a reference point, here are the results of the geometry experiment again. This is not a new graph, it's what you saw, just here again for comparison purposes. When I implement both the attentional tuning and memory components in the OWL learner, the agents show a similar pattern of results as the human participants, as you can see here. Another finding consistent with our hypothesis, but not represented in this graph, is that the agents make more memory errors when studying facts and more induction errors when practicing skills, which is consistent with the hypothesis that practice and study are emphasizing different information. As a further test, I elisioned one part of the model of the agents by removing the memory components. And as you can see in this graph in the middle, it destroyed the learner's ability to learn facts, especially when using practice only. Visioning the induction and attentional selectivity processes has the opposite effect. It's not presented here, but it impairs learning skills from examples. So overall, this modeling results suggest that the mechanism I propose is computationally plausible and likely to yield the learning behavior we see in humans. It also allows to further theoretical development. One thing we see in the AI agent is that erroneous responses are likely to be consistently tried when learning skills using practice, and that correct responses are likely to be forgotten and not tried when learning facts using study training. In sum, practice testing improves learning when there are no selectivity pressures, while studying examples occasionally boosts selectivity when needed. The mechanistic explanation implemented in an AI model of human learning involves encoding wrong information during practice of skills. So in essence, practice testing of skills increases the interference that gets in the way of generalization. I want to conclude by thanking you for being here and listening, and to my collaborators and funding sources. Thank you.